Well, good day, everybody, and welcome back. And we are starting a new unit, and this unit is on acids and bases. And we'll cover the basics of acids and bases, we'll get into some pH, and finally we'll talk about some titration. But let us get started with this consider. Consider an aqueous substance with the following properties. It is sour, okay, conducts electricity, and reacts with a group 1, group 2 metals to produce hydrogen. Is this substance more likely an acid or a base? So here we go. Let's talk about some acids and bases. And the first thing we want to do this time, which is kind of contradictory, not contradictory, but atypical, is that I want to just start with properties. Properties. What are properties of acids and bases? Okay, so acids, what are properties of acids, bases, and what are properties of bases? Okay, number one, let's talk about taste. Acids have a sour taste in general, and bases have a bitter taste. What else about acids? Well, they're going to react, as we know well, with group 1 and group 2 metals, sometimes other metals as well. You know, any metal above the hydrogen in our activity series, right? The acid will react with group 1 and group 2 metals and others, but not all, and others, to produce hydrogen gas, right? So number one, acids are sour. Number two, they react with group 1s and other metals to produce hydrogen gas. Group 3, they conduct electricity when dissolved. And number 4, they react with bases to form what? To form water and a salt. Now, salt is not necessarily sodium chloride. We think of sodium chloride as salt because that's what we call it at home, table salt. But really, a salt is any ionic compound formed from this kind of reaction, right? So I like to think of salts just as ionic compounds. Zoink, ionic compounds. So that means acids react with bases to form water and an ionic compound. In contrast to acids, we have our bases. Bases tend to be bitter. That's number one. Number two, they are usually slippery in an aqueous solution. So when they are dissolved in water, bases tend to feel slippery. 3, they do conduct electricity when dissolved. 4, zoink, what else? 4, oh, they're going to react with what? With acids, and when they react with acids, what are they going to form? To form water and a salt. All right, good. So that's our overview of acids and bases in terms of their properties. So let's go back and look at this question. I have something that is sour. It reacts with metals to produce hydrogen gas. What do we think this is? It conducts electricity. This would be, in all likelihood, an acid. Got it? Perfecto. That's easy. Moving on. Okay, consider dissolving NaOH and HI in water, and I get these kinds of reactions, right? Which of these is an Arrhenius acid and which is an Arrhenius base? Okay, now we're getting to my love, right? Definitions. Let's define acids and bases. Now, there are 3 definitions that we use in chemistry. There may be more, but the 3 big ones. We're only going to discuss 2. We want to discuss Lowry Bronsted, or Bronsted Lowry, depending on who you want to put first. And that's that. Whatever that is. That's what that is for Bronsted. Lowry Bronsted and Arrhenius. So there are two distinct definitions. Let's talk first about our Arrhenius definition. And we've already discussed this earlier in the year, right? An Arrhenius definition of an acid is what? It is a substance which increases the concentration of hydrogen cations when dissolved in water. And generally speaking, it takes the form of HX, where H, of course, is hydrogen, and X is a non-metal, or it can be an oxyanion. So when I look at the definition, when I look at examples for an Arrhenius acid, it's going to be something like HI or HNO3. Those are examples of Arrhenius acids. Now, what are my Arrhenius bases? My Arrhenius base is very similar, right? It is a substance which increases what? Concentration of OH minus when dissolved in water. Good. And what's the general form? The general form is going to be M OH to the Y, right? Where M is a metal and Y is the number of OHs in formula, right? In the formula. And that makes more sense when you see an example, right? I can have KOH, or maybe I would have MgOH2. But in any case, I have some OHs hanging around. And so those are my definitions for an Arrhenius acid and Arrhenius base. So let's go to our question. Which of these is an Arrhenius acid? Easy. The one that creates H+, so this is my Arrhenius acid. And then what is my Arrhenius base? The one that creates my OH minus. That's my base. And we, like I said, we did this earlier in the year when we discussed our naming of acids and bases. And I assume you still know how to do that. Good. So let us move on. Aha. Consider this reaction. I have hydrogen sulfate plus water creating dihydrogen sulfate plus, or also known as sulfuric acid, plus hydroxide. Identify the LB acids and the LB bases. Okay, LB. What do you think LB stands for? Well, that's going to be what? That's going to be our Lowry Bronsted. So let's bring our talk of Lowry Bronsted down here. So let's talk about Lowry Bronsted definitions. Bronsted. Okay, Lowry Bronsted definition of an acid. Are you ready? Acids. A Lowry Bronsted acid is an acid. It is a substance which donates a proton in a reaction. Okay, so we're looking at something that is a proton donor. Got it? A proton donor. Now, what is a proton? Well, really, folks, a proton is what? H+. So we're looking at something that donates an H+ in a reaction. So let's take something like this. I have HI, and we're going to have water reacting with it. And what that's going to produce is hydronium plus I minus. Okay. And what you're going to start seeing now, ladies and gentlemen, is with Lowry acids and bases, we're not going to write it just as HI going to H plus and I minus. We're going to actually have it react with water, which is closer to reality. And so instead of looking at H plus concentration, we look at hydronium. And we kind of use hydronium and hydrogen cation now interchangeably. But we'll start focusing, when we're talking about things that are acids, we're going to start talking about something that increases my hydronium concentration. Now, having said that, let's look at the transfer of the H+. How did hydronium get to H3O plus? How do I get H3O plus out of H2O and HI? Well, what happens is this H is going to be what? Transferred over here, right? Because now I'm left over here with I minus, and my H, where did it go? It went to my water to form hydronium. So my HI is doing what? It is donating a proton. It is a proton donor. And so from a Lowry Bronsted definition, HI is an acid. Good. What do you suppose a base is then, according to Lowry Bronsted? Well, it is a substance which accepts a proton in a reaction. Got it? So it is a proton acceptor, or an H plus acceptor. So in our reaction here, who is accepting the H? Or not who, what? My water is accepting the proton. So that means in this reaction, my water is the base. So my water is the base, and my HI is the acid. Okay, cool. Let's see, is that all we need to know? Oops. Which of these, let's look at this carefully. What's happening here? I'm going to OH minus. So how do I get from OH minus? Well, that means this H had to go where? It had to be transferred there. So who is the proton? What is the proton donor? This is my proton donor, which means it is the acid. What is my proton acceptor? Well, this is my proton acceptor for this, so it is the base. So water is my acid, and my hydrogen sulfate is my base. What is the conjugate acid? Okay, we need to know more stuff here. Let's go back and let's add some more things with my Lowry Bronsted discussion. Let's go through here and let's talk about conjugates. Conjugates. There we go. I can spell sometimes. Conjugates. Now I can have a conjugate acid, and I can have a conjugate base. Okay, so what is my conjugate acid? A conjugate acid is the substance which results from the acceptance of the proton. You understand what I mean by this? Okay, we said that there is a proton acceptor and a proton donor. What happened, my conjugate acid is the substance which results from the acceptance of the proton. So over here we said what? Water is my proton acceptor. What happens to water after it has accepted it? Well, after it accepted it, it becomes what? Hydronium. So that means this is my Lowry Bronsted base, which makes this its conjugate acid. Okay? This is the conjugate acid. It is my water after it has accepted the proton. Then what's my conjugate base? Well, it's going to be the substance which results from the donation of a proton. It's what's left over, what's left after the proton is donated. Proton is donated. So let's go back. Let's see what's doing the proton donating. This is donating, right? So that is my acid. What's left after that hydrogen is donated? Well, my I minus is left, right? So that means this is the acid, and my I minus would be the conjugate base. Okay. And what's important to know here, right, is for every LB acid, there is what? There is a conjugate base. And for every Lowry Bronsted base, what? There is a conjugate acid. Not only that, for every LB acid, remember, for me to have an LB acid, I must have a proton that is being donated. Well, if there's a proton donator, what must there always also be? There must always be a proton acceptor. That means there is always a Lowry Bronsted base. In every Lowry Bronsted acid reaction, there must be a Lowry Bronsted base. Got it? And we'll get a hold of this as we look at our examples. Good. So here we go. Let's take a look at this. Here is my Lowry Bronsted acid. It donates the hydrogen. What's left over after it's donated? Well, OH minus. So if this is the acid, this is the what? The conjugate base. Good. And if this is the base, right, after it accepts a proton, what do we have? We have this thing, which means that here's my base. So this must be what? My conjugate acid. Got it? Perfect. You guys, let's see, to answer all these questions? Yes. You guys answer these, bring me back. Well, we want to follow the flow of the hydrogen. Notice over here, I start here with water. I end with H3O plus hydronium, so what must happen? That means this hydrogen must have been donated here. Good. If that is donated, that means my acid is HSO4 minus. What is my base? What's receiving the proton? HOH. What's my conjugate base? Well, let's look at what happens after the hydrogen has been donated. What am I left with? SO4 2 minus. And after my water has accepted a proton, what's left? What results from that? Hydronium. So there we go. My acid is hydrogen sulfate. My base is water. My conjugate base is sulfate. My conjugate acid is hydronium. Now notice these things can work in reverse too. Let's look at this side of the reaction, right? What happens to my hydrogen? Well, I take a hydrogen and it's donated here, right? And this is what I end up making, and this is what I end up making. And so that would make my hydronium a Lowry Bronsted acid and my sulfate a Lowry Bronsted base. Hey, just like our conjugates suggest. Now notice also what's kind of cool here. In this reaction, water was a base, right? But in this reaction, what was water? Water was an acid. So whether something is an acid or a base from Lowry Bronsted all depends on how it's used in the reaction. Got it? Okay, moving on. Aha, let's look at this. I have hydrogen iodide, reacts with water, forms my hydronium, and I minus is hydrogen iodide. What do we call that? Iotic acid. Is iotic acid a strong acid or a weak acid? Okay, we want to add some more notes here. Ooh, where do we go? I think we're going to take blue right through. Let's go this way. Oh, too low for me. How low can you go? Too low for me. Good. Change key. There we go. Strong versus weak. Right? We want to talk about differentiation or categorization. Strong versus weak acids. And that means, of course, we're going to have strong versus weak what? Bases. Good. And what are my strong versus weak acids? Well, remember, this goes back to electrolytes. Strong acids, a strong acid is what? A strong acid is an acid which is a strong electrolyte. Good, and we all remember what a strong electrolyte is. It's something that dissociates completely into ions, right, when dissolved. That is my strong electrolyte. And an example is what we had up there. Hi plus water yields what? And that's aqueous, liquid. And I would form hydronium aqueous plus I minus aqueous. And notice it's a one-way arrow, meaning this Hi breaks up completely into ions. So it is a strong acid. And what are my strong acids? Well, I like to start up here with HCl and work down my halogens. HCl, Hi, HBr, right? Those three. And then I go to my nitric acid. And then I go to my chloric acid. And then I go to my perchloric acid. And then I have my H2SO4, which is a special case. The first hydrogen is a strong acid, okay? So hydrochloric acid, hydroiodic acid, hydrobromic acid. This is called what? Nitric acid, chloric acid, perchloric acid, and sulfuric acid. Those are my strong acids. Good. What are my weak acids? Well, a weak acid is what? It is an acid which is which? How about spelling which, right? Which is a weak electrolyte, right? And that means it forms an equilibrium between its molecule and its ions, right? So we take something like nitrous acid. We have an equilibrium between this ion, and that molecule, right? And those are my weak electrolytes. And how do I know them? Hey, all other acids, we assume, except these guys. So memorize them, and if it's any other kind of acid, then it's a weak acid. What about my bases? Bases, whoops, bases. Well, we're going to have two types of bases, aren't we? Right? We're going to have weak bases, and we're going to have strong bases. And what do you think of strong bases? Strong base is a base which is a strong electrolyte, and a weak base is a base which is a weak electrolyte. And what are my strong? Well, they're going to be really all hydroxides, all metallic hydroxides. Now, there's some debate within my colleagues that, well, it's really group 1 or group 2 hydroxides. Other people say it's all hydroxides because remember, strong electrolytes are what? Any ionic compound, and all of my hydroxides are going to be ionic. So these guys are all strong electrolytes, so they would be strong bases. Yeah, someone might say, hey, well, zinc hydroxide is not very soluble. That's true, but that amount of zinc hydroxide, which does dissolve breaks completely into ions. So that would, even though that has a low solubility, it is still a strong base, according to me. So all your metal hydroxides we are going to consider as strong. And there are several weak bases, but the only one I care that you know about is ammonia. Okay? Cool. All right, let's go answer our questions. Let's see there. Nope, right here. Is this a strong or a weak acid? Hey, it's HI. And I look, it's a one-way arrow. We know that's strong. Good. Let's go to the next thing. You guys figure this one out. Oh boy, this is easy. It's a weak acid. You write the reaction. Well, here you go. HNO2 plus water. That's a liquid. This is aqueous. It's a weak acid, so that means I have equilibrium arrows. I have a reversible reaction. I make hydronium, and I make the nitrite anion, oxyanion, and it is in equilibrium. There we go. And then the last, you guys do this. Consider the weak base ammonia. Write the reaction. Well, I'm going to have ammonia, right? And it's aqueous plus water. And we know it's going to form something. Now, if it's a weak base, what does that mean? Well, it must be what? A base is a proton, what? Proton acceptor. So in this case, it must accept a proton, meaning this must be transferred here. It means I'm going to make ammonia. This is my conjugate acid, right? That's my conjugate acid. And what else do I make? OH minus, right? Aqueous. Good. And it is a equilibrium system. So there you go. That's my weak base ammonia going to form ammonium and hydroxide. And I think that's good for today. Next time we're going to get into the autoionization of water. All right. Have a good day. Be good.